Hello and welcome. Today I wanted to show you on how to measure the motor pull number via our digital motor controller and the program Endrive by either using the phasing rotating process or the special function identification of motor pulls. Our system setup consists of a Bamocar PGD3400-400RS inverter and an Emrax 208 high voltage motor with a special Tamagawa resolver with 5 pole pairs. Of course, Emrax inside their datasheet, they specifically state their motor pole pair number with 10, which is great. So basically, this tutorial is useless, but a lot of times the motor pole number of especially of a permanent magnet synchronous motor is unknown. And I'm just using the Emrax motor for demonstration purposes. I have set up a little camera where you can see my Emrax motor. I have used a little sticker so you can see the actual position before we start the special tuning processes. As stated before, we already actually know that the motor pull number is 20, but in our case, let's assume we do not know it and we have a random number, for example, 16, and we need to try to identify the motor pull number with either the phasing process or our special tuning algorithm. First, I'm going to show you how to figure out the number using the phasing process. With the phasing, if you go on the page tuning, and you have limited the AC current output before you start, which is very important. Basically, what happens during phasing rotating, the motor will rotate from motor pole to motor pole as many times you have entered a value. In this case, it will do 16 divided by 2. It will do 8 jumps in total. And the goal is to find a motor pole value which will create a 360 degrees turn of the motor. So let's test this out now. I'm going to start. I'm going to enable the drive. It will jump into position and then it will jump from one pole to the next with a total amount of 16 times. And as you can see, it has not reached our 360 degrees, meaning it still requires further jumps to reach it, so we know that this value of 16 is too small. For example, if I use the value of 24 and I repeat the phasing rotating process and we have a starting position down here now, you can see that it has rotated too far, indicating us that this number of 24 is too big. And using the correct pole number of 20 and repeating the phasing process, it has rotated 360 degrees, showing us that our value of 20 is correct, which we then can save. And after enabling the motor, we can try and test, and it actually has worked nicely. The controlling works as intended, both in positive and negative direction, showing us that the initialization configuration is correct, and especially the motor pull number is correct. But there's a different way, an easier way. For this case, I'm gonna set up a faulty motor pull number again. It is the identification of motor poles algorithm. But in order for this to work, it is very important that the feedback pole number of your resolver is correct. if you have an incremental encoder, your incremental value must be correct for this to work. So meaning the feedback has to be set up correctly in order for this algorithm to work as intended. We know a motor pole number of 10 is incorrect, but we know that the feedback is set up correctly. So we go back to the tuning. We select the identification of motor poles. We start. We enable the drive. It will rotate from one pole to the next and measure the delta value of the increments. It will tell us to disable the inverter. We will disable. Sometimes we will get an ADC measurement problem warning. We can just ignore it and clear it. We can save it to the drive. We can reconnect for the parameters to be loaded again to the N-Drive software. And as you can see, it has jumped from 10 to 20, showing us that the new pole number of the motor configuration is 20, which is exactly what we wanted. Great. I hope this video has helped you. More videos will follow. I wish you all a happy and nice day. Happy controlling. Bye.